Hi, welcome everyone. I see you are joining. We will wait a few minutes before we start. So we give time to everyone. Okay, I can see it. All right, let's maybe just give, okay, just another minute. Okay, okay, I would say maybe we can start and people will still can join. Okay. So, welcome everyone. Thank you for being with us. I am Chiara Serio. I work at Icons, and we take care of communication and dissemination of European projects. And today we are here for eNeuron project. eNeuron project is a project that works on local energy communities and in particular tries to develop tools in order to optimize the energy hub operations. So today we are here with Dimitri and Gianluca. So they are gonna talk about in detail. Dimitri is from SINTEF and is gonna present a little bit the project and the tools that he developed together with his colleagues. And Gianluca is also going to go more into the detail to explain indeed how this energy hub works. And then we are also going to showcase some of the tools that have been developed. At the end, there's going to be a Q&A, let's say a questionnaire that we want to have with you. And of course, it's going to be anonymous and it's going to be GDPR compliant, so don't worry about that. Yeah, so just to explain a little bit what we are using, GoToWebinar. It's similar to Zoom, so you will find a way to open your mic if you want. You can find a chat where you can indeed put all your question if you want or your comments. Yeah, and if you need technical support, you can indeed write in the chat, and I'm gonna help you with that. So, okay, without further ado, I leave the floor to Dimitri. Yeah, thank you again for being here.
Hello, everyone. Let me just share my screen. Okay, is it? Do you see the screen?
Yes.
Okay, thank you. Okay, so in this presentation, welcome everybody, first of all. In this presentation, I will go over the eNeuron toolbox and the concept behind it, with a special focus on the energy hub level tools. So with energy hub, we mean local energy system, but not at the appliance level. It's more larger units or aggregated consumers or single larger consumers, but not going as low as simple appliance control. So if you want more information about the rest of the toolbox and specifically the micro energy hub level, please refer to the website where you'll find information about the whole toolbox. So In this presentation, I will first go through the concept diagram, then I will go through SINTEF's tools inside the toolbox at the Energy Hub level, and then my colleague from ENEA will present ENEA's tools also at the Energy Hub level. So we can, here you can see the concept diagram, and you can already notice that it is divided in different sections. So you can see on the top is the Energy Hub level, while on the bottom is the Micro Energy Hub level. So it might be a lot of information for now, but I will guide you through it, so you don't need to try to decipher it by yourself. Another thing you can notice is the 3 different colors. In blue is the planning phase, so long-term strategic planning. In red is the day-ahead planning, and in green is the Micro Energy Hub level and the real-time phase. So we can zoom in into the Energy Hub level, and the entryway into the Energy Hub level, one of the possible entryways to specify your energy systems is external data that you use to specify your energy system inside the toolbox. So that's where you will input different relevant parameters, what kind of assets you have inside your energy system, etc. Some of this information might need to be processed. So we have a specific tool for processing this information and creating specifically for time series and historical data to produce representative periods that can then be used inside the long-term planning tools. So this previous box, the processing box, I will come back in a few moments, and also this one I will also give more details about SINTEF tools in this box. So there is also a tool from ENEA that will also be presented. So from this blue part, what we get is the long-term strategic planning. So you have defined the energy system that you may already have in place, or an energy system that you're planning to develop, and you are looking into what can you do in the future to improve your energy system, to improve the profitability, reduce the costs, improve the energy system in terms of environmental criteria, for instance. So this part will take care of this long-term planning. Then we can move on to the day-ahead planning part, which also takes in information. So maybe forecast information about irradiance or other kind of forecasted time series. You can also get some information about from measurements from your system that can be fed into forecasting tools to assess and to give input data for the operational analysis. So my colleague from ENEA will give a more in-depth presentation about the tools involved here. But this step allows you to look at how to optimally use the different assets inside your energy system to, again, minimize the cost of the operation or account for environmental criteria. And it gives you the optimal operation for your energy system in the next day. Then, moving on from the Energy Hub level and into the Micro Energy Hub level, this information arrives into the peer-to-peer market, and I will come back to this. So at that Micro Energy Hub level, we also have inputs from forecasting services at a higher resolution that also provides information for the cloud-based solver and peer-to-peer market that are together based on the information from the Energy Hub level and the day-ahead planning decisions that were made to refine it for real-time timescale. So finding the optimal operation of the different assets. So then this information about how to operate the different assets can be exchanged in real time with the assets themselves, and the assets can feed back their state into the solver so that it can be taken into account for the computation and the peer-to-peer market as well. So that was just a very short introduction to the eNeuron concept and the what can be done inside the eNeuron toolbox. Now I'll move on to the way we implemented this toolbox and how the different tools are integrated together. And then I will move on to SINTEF tools at the Energy Hub level. So regarding the tool integration, there were different problematics that needed to be resolved. We have different tools. Some were existing in some state from before, and some needed to be developed in the project, and we needed a way to make those tools work together. But those tools might be developed in different programming languages. They have different IP restrictions, so it's not trivial to make them work together. And we also want to have a system that's easy to start using. We investigated different possibilities for achieving this. So one of the solution is would have been a solution similar to what was used in another European project called OpenENtrance, which is a scenario explorer. So in their case, they set up a scenario explorer online, so a website where you can access results from different models, and you can also interact with the platform and retrieve information. But it was focused mostly on European scale tools, and also the main focus was giving access to results to as many people as possible and allowing people to explore results. So it's not exactly the same problematic that we face, so we assessed it to not be the optimal solution for us. We could also have developed APIs for each of the tools to allow each tool to make calls to the other tools. But this solution would have been heavier to implement, and also might not have been adapted to all the tools that needed to be integrated together. So what we ended up choosing is a tool that was developed also in another European project called the Spine Toolbox, which provides exactly this, a framework and tools to facilitate the collaboration between different tools through the use of workflows and the exchange of data through database. So using this tool, you are able to set up workflows where you can import the necessary data, run your tools that may be in Python or in different languages, and then posts this data to a database. It also allows to have a version control of the workflows and of the database itself. And it provides a graphical user interface which facilitates its use. So now, moving on to the main tools at the Energy Hub level, I will focus on the data processing and the SINTEF tool for long-term planning. So for the data processing and for preparing representative periods for the long-term planning, we developed an open source tool that is included in the eNeuron toolbox, but can also be used outside of it, which is based on the SciPy package, which is also open source, and makes use of hierarchical clustering and word linkage for those that are interested in more details. So it's a kind of generic clustering tool that give you flexibility in the type of clusters or representative periods that you want to produce. So you can produce representative days or over cluster shapes. So if you want representative weeks or a different time scale, you can also do that. If you are using days, you can or you can also have representative periods per season. So the user can define his own seasons. You don't need to stay and stick with 4 seasons. As we know them, you can define the seasons or the segments in the year that you want. And if you use representative days, you can also include a differentiation between weekends and weekdays. So this tool will be also quickly shown during the demonstration that comes after the presentation from my colleague. But now the next tool that will also be included in the demonstration is the tool, the SINTEF tool for doing the strategic planning. This tool is also called Integrate or SINTEF 1 in the context of the eNeuron toolbox. And to give you a very brief overview, it's software for planning of local energy systems, which has its own graphical user interface to facilitate its use. So you can build your energy system inside the model by drag and dropping the different components, and also see some of the results directly inside its interface. It's built in C++ and use MPL for the operational optimization. The tool can and is designed to work with different energy carriers to be able to be adapted to as many energy systems as possible. So the way the program works is that you first define the energy system in its current state. So if you already have an energy system, or it can be, it's not necessary if you have, if you are planning a new energy system, and then you can define also the investment options that you want to consider throughout the years in the horizon you're interested in simulating. And to give some technical details, the operation of the system is then optimized in a linear program or a mixed integer linear program, depending on which components you have added to your system, for all the different possible states of the system. So that means the different years, the different representative periods, as well as the different combinations of technologies inside your system. And then dynamic programming approach is used to find the best investment path throughout the years. This approach also allows to model investment logics, such as linking investments together. You can say that if you invest in this given investment in 1 year, then the following year you need to have this over investment. Or you can have mutually exclusive investments, for instance. It also allows to and provides not only the optimal solution, but also solutions close to optimality by you can define a certain number of ranks and solutions that you want, and it gives you the optimal solution, but also other solutions that are close to being optimal, but that you would not necessarily have been able to visualize otherwise. So this will also be shown a bit more inside the demonstration, but for now, that's it for SINTEF tools, and my colleague will take over to present you the tools from ENEA at the Energy Hub level. Thank you.
Thank you, Dimitri. Gianluca, now we will make you presenter so you can share the screen. And Dimitri, there is a question in the chat, but maybe for the sake of time, we tackle it later, okay? Okay.
Yes.
Gianluca, now you should be able to share your screen. Yeah, we can see.
Okay. Okay, thank you, Chiara and Dimitri.
Yeah,
hello,
Gianluca, if you want to share your PowerPoint, we do not see your PowerPoint now. Huh? Oh, now we see it. Okay.
Hello, everybody. I'm Gianluca Sforza, computer scientist at ENEA. I am part of the group who developed the optimization tools. My focus is on their integration in Spine. So I will describe the tools at energy hub level for optimal design and operation, and tools supporting these optimization tasks. Finally, I will talk of the integration in Spine workflows of these tools. So the eNeuron toolbox consists of a set of integrated tools for optimal design and operation planning of integrated local energy communities, the ILEC short. Innovative approaches and methodologies were developed to optimally plan and operate ILECs through the optimal selection and use of multiple energy carriers, and by considering both short and long-run priorities. As illustrated in the figure, the operation of energy hub level consists of two phases. The planning phase, here, to provide optimal configurations for system design or system expansion of an ILEC. And the second phase, the operational phase for analyzing different operational scenarios and performing day-ahead scheduling of the distributed energy resources in the ILEC. The design optimization tool determines an optimal combination of technologies, including factors such as type, number, and size. This tool receives a predefined superstructure of the ILEC in terms of candidate technologies and energy interactions among them, to satisfy the ILEC multi-energy demand. The objective is to minimize the weighted sum of total annual cost and total annual carbon dioxide emissions. The multi-objective function determines an optimal combination of technologies in the multi-carrier energy system. Based on system design, technologies and their characteristics in the planning phase, the previous one, the operational optimization tools optimize the dispatch of multi-carrier energy hub by following multiple economic and environmental objectives. Please note that the operational analysis can also work standalone by directly interacting with an ILEC configuration given by the user. Here, two tools have been developed. The first tool, by adopting a multi-objective optimization framework, takes input data such as user demand, local climate data, energy prices, and technical information of the energy technologies to determine the optimal operation scheduling of the multi-energy system, by considering also the uncertainties related to renewable energy sources and about energy prices and user loads. Two approaches were implemented: the deterministic approach, which uses day-ahead forecasted data, and the stochastic approach, which takes into account the scenarios related to uncertain parameters. Second tool instead provides a comprehensive, again, multi-objective optimization model for this time for optimally managing electric vehicles with grid-to-vehicle and vehicle-to-grid technologies. Other tools have been developed to support system design and operational analysis tools. Dimitri before introduced the data processing tool that allows clustering historical time series into a set of representative days to be used by the system design optimization. So this tool is provided by SINTEF. In particular, it carries out generation of representative days related to energy loads, energy prices, and renewables availability. Prior to the optimal operational analysis, it is necessary to prepare data and make them compatible with the operational analysis tool. Two approaches are included to determine renewables generation and load profiles. The day-ahead forecasting to forecast data for the next day that is required for scheduling the day-ahead operation of the system. Here there are two tools, one provided by FOSS for photovoltaic generation, and another provided by ENEA for load. They are other partners of the project. Second approach, scenario generation, consists of the generation of scenarios to be analyzed in order to verify a given system configuration under various operational conditions. And this tool is provided by SINTEF and ENEA. So we have seen that the functionalities of these tools are complementary. So all these tools need to exchange data. Since the focus at the energy hub level is on analysis, that interaction between tools is not that sensitive to latency issues. Therefore, it can be organized through a shared data storage as the Spine database. In this case, then, Spine gives an environment for integrating the tools. So the question was how to know the parameters a tool requires, which are provided by other tools. I will introduce, to answer this question, I will introduce a methodology we devised to document the integration of the different tools in Spine. This table, these two tables, answer the question how to know the parameters a tool requires that are provided by other tools. So the table was created to track links between cooperating tools exchanging data. The first table on top gathers output data and their destination. As you can see, columns C and D, while the second table at the bottom collects the input parameters and the origin of these parameters. So there is a match between these two columns. As you can see here, a specific nomenclature has been adopted. For naming the variables. So first there is the scope, then the tool name, the link, and eventually the parameter's name. And this is an example of a Spine workflow. Actually, this was selected for the sake of clarity as the simplest of the three workflows we developed. So it illustrates the workflow for design optimization. This is the whole picture, and here a zoom. So we said that tools interaction happens by means of Spine workflows. And there is a one-to-one match between the previous tables you've just seen and the Spine workflow. What are the main steps here? So first, data are retrieved from the shared database and from local files if available. This is done using an export component provided by Spine. Then there is a mapping between external names used in the database to internal names used in the workflow. And this is accomplished by means of transformer and database components. After these data are pre-processed by a Python script before feeding the optimization tool. And this is done by using the tool component of the Spine Toolbox. After all these steps, eventually we can run the tool and collect all its outputs and import them into the database using an import and again database components. Import and database components. So where all data are collected? Data are sent by Spine Toolbox to a remote MySQL database that is managed by Spine. The communication occurs through the exchange of CSV or XLS files mapped on the Spine database, which has its own internal logical structure. The data structure we have used to store data is the map. A map includes, as you can see in these examples, a map includes multiple indexes. So here you can see the specification mask for an importer, for an exporter component, and a view of the Spine database. The optimization models embedded in the tools have been implemented in CPLEX, a decision optimization software that is property of IBM. For enabling data exchange between Spine and CPLEX, an open source Python library called do-OPL was used. OPL stands for Optimization Programming Language. Data retrieved from Spine database or from the local file system are exported into CSV files that are first converted into tuple sets, data structures, and then passed on to the corresponding variables of the model. The Python script selects the last occurrence of a parameter that was inserted in the database, leveraging the default behavior of Spine Spine Toolbox, that is, when importing data in the database, it saves the timestamp as an alternative name. Just a curiosity, wasting lots of time here. Spine reproduces the path, the path structure of input-output files in its own working directory at the runtime. And this is to mimic the same paths used in the script. Thank you.
Thank you, Gianluca, for your presentation. I think we can show the demonstration video, but we'll focus on the SINTEF tools and showcase the use of them. Thank you.
Yeah, indeed. Now we will share the video. So and then we will tackle your questions. We have 3 questions from the audience. So thank you for your questions. Okay.
Welcome to this eNeuron Toolbox demonstration. In this demonstration, we will show you how you can use external data and build a representation of your energy system inside our tool and our toolbox, and how we can study the future planning of your system using SINTEF and Integrate. So we'll take external data, process some of the data through our clustering tool, and then take this data inside the graphical user interface of SINTEF 1, where we can conduct this kind of studies. Then we will take the results and the relevant parameters and export them for use further inside the toolbox in the rests. So we will just use a very simple example of an energy system with simple components. I will just quickly show you other types of components that can be used inside Integrate. I will also show you how input data can be processed through clustering and taken inside Integrate easily, and then how the results are processed and exchanged to the database. So let's move on to this view. And here is Integrate's graphical user interface. So I've already built a simple case with a grid connection, a battery that is defined as an investment option, an electric load. So all the ones in dashed lines are investment options. We have an electric boiler, a heating load, a gas boiler, and a gas market. So you have a lot of different components. So conversion components like CCGT, heat pumps, CCHP, district heating components, electricity components, etc., cooling components that you can drag and drop. So I can take one, and then you can input some input data and build your system this way. So I've already pre-filled some of the data. You can also define the number of time steps. Let's say it's set to 24 hours. The years, where you can define also different parameters for example, coefficient for the evolution of the load through time. In this case, we'll leave it like that. And you can also define, for instance, your segments. So I've defined 4 segments. I've left the weight to 1. The weight should be equal to 365 since we're using representative days in this case. And it's also here that I defined the investments. So you can define the investments and then assign it to one or several of your components. So there's a lot more possibilities, but it's just a quick demonstration. So here's our system. So now we are still missing some of the input data. So if we look here, we see the electricity costs, which are profiles for each representative periods are not included. We can do the same here for the load. In different periods, it's empty. So you see it's just default data. So we need to produce that. To do that, we are going to use the clustering tool. So the workflow program had closed, so now it's reopened. So here we are in the Spine Toolbox, which allows to create workflows and facilitate collaboration between different tools. So you have local workflows that communicate to a common database, facilitating the interaction between different tools. So here we have our clustering tool. We can have a look here. It's also open here in Spider, but you can run it directly through Spine Toolbox. It's already set up like it should be with the correct input data. So we can just run it. We can see, yeah, so let's purge the database so that I can show you that it works. Okay, so it's purged. Now let's look. It takes a little bit of time to do the clustering. I can show you in the meantime the input data that goes in. So we have, here we have a configuration file that defines the different seasons if you want to use seasons. So in this case, we're using one representative pair per season, but you don't have to. Clustering is maybe not strictly necessary in this case, but you could define more periods per season, and you could define a differentiation between weekends and weekdays, for instance. We also have the clustering input, which in our case is the electricity price, the gas price, and the loads. So for one full year. So now it's finished. We can have a look here and we see, okay, it has been uploaded. We have our different representative periods. So we can have a look at the spring or the winter, let's see, for the space heating in the winter. And we see, okay, we have a representative array and we can look, okay, it's not the same, it's 0 for the summer, for instance. In the autumn, it's a different value. Okay, so now we have those clusters. So we need to take them inside our model. So to do that, we'll start by exporting our model data. So it will produce different files that contains our model, basically. Then we could do it inside a workflow, but we have it set up here, where it will modify the files that we have retrieved from Integrate now with the correct data from the clustering. Okay, I forgot to copy the results of the clustering to the correct place in this case, since it's not inside the workflow. So let's just retrieve it so you can see that's the correct timestamp. We can take those two to the data and run again. Okay, now it worked. So now back in here, now those files have been modified and we can import them again to modify the data. So we can start with the segments parameters. So we are here. Parameter segments, and okay, so we can wait till it comes back. Sorry. Okay. Save. Let's see if it has been modified in the segments. So okay, it didn't seem to work this time. So sometimes it's a bit capricious. So let's try again. There's no reason for it to not work. Okay, now it's good. So now the correct values have been added for the weights, and we also want to import the time series, which were, as you saw before, not specified. So we can go back to the same place and retrieve the time series, so parameter series, and okay. So now let's let it load. Okay, it's back. So let's have a look at the data. Now we can see that where there was no data before, now we have time series, and they should be different. So here we have in 427, for instance, and if we look here, it's 25, and it corresponds to the correct data. And if we look the heating load we saw earlier, it was quite high in the winter, and we find it again here. Okay, so now that worked. We have imported our data and time series, so everything is set up correctly in the model. We can just run the model. So you have different options. I will not go over them, but you can link investments or make mutually exclusive investments, for instance. But now we just want to run it normally, so it will take a bit of time. Okay, so now the model is run. We can see here some information about the different operational runs, etc., and that there is no error message. And here you can see results directly in the graphical user interface. So we can see different ranks for the electric boiler. So in the optimal solution is to just invest in an electric boiler in 2020 in this case, and in the second optimal after that is to invest in a battery in 2025. So you can look at the investment costs, which are here really low compared to the operational costs, so you don't see them so well. You can also look at, so for instance, we saw the battery is invested in 2025. So let's have a look at the battery in, let's say, the autumn in 2025. And we can see, also it was in rank 2, of course. So now we can see the operation of the battery, or at the losses. So you can see the battery state here. Okay, so now we have made the model, we have run it successfully and have results. So we can export again this data. Let's say to the same place. Now that will include the results. Okay, so this can now be, we can now copy those files to the folder corresponding to the next workflow that we're going to run, which is the one uploading to the database that then can be retrieved by other people. So let's make sure that it's empty. It's not empty, so let's purge it. Purge. Now it is empty, and it should already be set up all correctly. So we can just let's make sure. Yes, I think everything is set up correctly. So let's run it. So now we are retrieving this information from the different files, the results and all the parameters that might be helpful for other workflows and tools in the eNeuron toolbox, and making it available for them. So we can, for example, display our energy system, so it's a bit organized a bit differently, but you can see that we find the same components. On the right here, we have the heating part with the gas market and the electric boiler coming from the electricity part on the left. So we find again the same elements, and we can have a look at results, for instance, if we wanted to look at let's see what we can look at. Yeah, the battery charge in the rank 2 in this segment. So it's not exactly the one we had looked at, but you get the idea. You can get the same kind of results. You have the same result that we saw earlier inside this database. And then now it's in the database, so other tools can use it. If you have a different use case where you need this data, you can retrieve it and make use of it. So that was it for this presentation. I hope it was helpful in understanding the eNeuron toolbox at the Energy Hub level, and thank you for your attention.
Let's tackle the questions. There were 2 questions for you, Dimitri. So I'm going to read them, and then you can answer maybe very quickly, and then we let everyone go. So one question was, regarding the day-ahead calculation of the optimal dispatch, do you consider uncertainties regarding the forecasts, and how do you deal with for the optimal dispatch calculation?
So maybe that's a question that Gianluca could answer better, but the tools from ENEA can handle the stochasticity in the inputs. Maybe Gianluca can say a bit more about which stochasticity you consider. Or maybe that question was from before Gianluca's presentation, so maybe it was answered during his presentation. But
it was indeed before. Yes, it was indeed before. Gianluca, do you want to comment, or I read otherwise the other question, which is regarding real-time management. What is the definition of real-time? Does forecasting and cloud solvers not conflict with real-time control requirements?
So for this question, I'm not the best person to answer, as I'm more focused on the Energy Hub level. So I would refer you to my colleagues from ENEA who can provide you all the technical details that you would want. So maybe we can provide you with email addresses to our colleagues who are focusing on this real-time part, and they can provide you with a precise answer to your question.
Yes, and also for the previous question, if they want to drop an email, we can answer properly. Anyway, uncertainties or scenarios are managed, but I'm not sure I've got the question.
Okay, so if Chris wants to leave his email address, then great. And I thank you everyone for being with us. You will find also more information then and the recording on YouTube, and so you can just follow eNeuron social media or eNeuron website, and you will find an update about what we do and the toolbox and all the tools that we've been developing. So thank you a lot and goodbye, everyone. Thank you. We will now end the webinar. Bye-bye.